Hey Tom, do you run into a lot of questions about the NEC code?
Well, Dan, you know, Article 250, grounding and bonding, that's a big area where there's a lot of confusion, and you'll get a lot of debates even at the code panels amongst engineers and installers on all the different terms that we have to use and getting everything the same and everything right. It's a target-rich environment for questions.
Rick, how about for electricians? I mean, is it really pretty straightforward, or do they kind of know what they're doing?
We run into a lot of confusion about grounding and bonding as far as transformers, bonding XO, when to bond, where to bond, with the different starts and stops of service, earth ground, building steel, foundation grounds. There's a lot of confusion based on that.
I mean, I see it with power quality. It's like, you know, if it's 3-wire, 4-wire, transfer switches, all this kind of stuff, even coming down the pole, going into the resi room here, where do we ground it, where do we bond it? I mean, at the end of the day, if a power quality person says they don't understand a problem, a lot of times, or if they act like they understand the problem, but they really don't, they might say, oh, it's grounding related, and they kind of just move on. That's a problem for me.
It's very confusing as an electrician to take the theory and apply it into the actual applications. So the more hands-on you can get with it, the better we can all become as installers and engineers, and more problems will get solved ahead of time instead of after the fact.
There's a lot of theory there. Getting your hands on equipment in facilities that provide that ability in an electrically safe, controlled environment, that's the key. That's where the rubber meets the road, actually seeing the fittings, seeing the bonding, and all of the meeting the National Electrical Code and practical application of grounding and bonding. It can't be replaced.
I agree.
Why are we talking about this? Why do we worry about grounding and bonding? We're worried about, and we want to establish an effective ground fault path, and we also want to think about those touch potentials or step potentials for two different reasons. First, the effective ground fault current path, we're intentionally constructing a low impedance conductive path that's designed to carry the fault current from the point of where the ground fault occurs in the system back to the source. And the reason we do that is we want to make sure that we open the overcurrent protective devices, which could be equipped with ground fault protection of equipment or GFCI protection. We want to make sure that we open those and give enough current for those to detect that fault. Now, you want that impedance to be as low as possible because we want to drive the fault current as high as possible. We have to understand the basic principles of ground fault currents will flow anywhere they can get a chance to. We're not going to guarantee that only the fault currents will flow through the equipment grounding conductor. And that's why we can't make the mistake of thinking that this grounding and this bonding will prevent someone from the electrical hazards of shock. When we talk about those electrical hazards of shock, we want to reduce our touch potentials or our step potentials. We want to keep everything at the same potential and be like that bird on a wire. So we expand this concept. If you think about the concept of touch potentials or step potentials and keeping things at the same potential, you can think about this in regard to substations, where we establish that grounding grid underneath the substation, or around swimming pools, where we're doing equipotential bonding. This will reduce the likelihood of voltage potentials, and we understand that a potential difference between two voltages is what's going to drive current. So if we can reduce or eliminate that potential difference, we can reduce the likelihood of shock, so we can reduce the likelihood of damage to electrical equipment.
With respect to grounding, transformers are often an area of concern and discussion regarding when, where, how, and why to ground the transformer. This is a simple single-phase example of a transformer like a 480 to 120 volt control power transformer. Considering the secondary windings, one of the two legs, typically X2, would be connected to ground. This would allow you to establish a reference to a known reference on the secondary of the transformer when this is required for safety, power quality, or by NEC requirements. X2 is also considered the neutral conductor for typical low voltage applications and would only be grounded at the transformer and at no other point downstream on the circuit fed from the transformer. For this situation, a simple wire connecting X2 to the incoming ground wire coming from the primary of the transformer would suffice for a control power transformer. This ground would also be bonded to the transformer case to ensure that the case and all metal parts remain at a constant potential for reference to the known ground conductor. I've seen many instances where this ground connection was not done to supposedly make it better for power quality reasons, but yet it almost always made it worse without the ground connection, and electrical equipment was damaged. Why do we only connect ground once? Well, if we incorrectly ground the neutral downstream of the first connection, here's the problem. Load current will return on both the neutral and the ground conductor, which is connected to all the metal parts in the system. For that reason, current will divide at the subsequent neutral to ground bond, and load current will flow in the ground. We absolutely don't want current to flow in the ground conductors unless there's a ground fault. Having a single neutral to ground connection ensures that this will be the case. In this next section, we will explain how this applies to larger three-phase transformers.